is that there will be 4 free response, 1 from each exam. And then remember, I told you what's going to be the first free response. Your first free response is going to be this question right here, where I only give you parts C and E. So of course, you have to do most of the steps. Actually, you have to do all the steps except for finding the angle. But just make sure that you can do those. I really want to see that you can do that vector math for C and E. And we can work through that if you want. Test 1, question 1. Those are the first 2 questions on the exam. But otherwise, oh, and then also, you know, I'll take this, and there'll be this a similar setup. That is, it'll be a setup that has 2 vectors, one that's off axis, but they could be rearranged in a different way. But they would definitely have 1 on axis vector and 1 off axis vector. So the math would be really similar. It's just the numbers are going to be different. And then you'll have 1 other question from each of the exams of the free response, but it could be any one. So for example, if I gave you number 1, I would just give you 2 of those. Or if I gave you this one, I would just ask you 2 of the currents. Each question only has 2 parts. Or if I give you this one, well, that one already has 2 parts. But don't say, oh, it's going to be that question because it has 2 parts. I'll just trim it down and ask just a couple of parts of it. And then there are 40 multiple choice. So those are, it is less than twice the length of an exam, but you have, you know, 2 hours for that exam. Because usually it's 28 questions, and now it's going to be 48 questions. Okay? There are 10 multiple choice questions from each of the 4 exams. And as I go through those, what I do is I pick the questions and then I change them in various ways. So for example, if I pick number 7, for example, not saying that it's on the exam, but just for example, on that question, really all that I would do is to change probably the slope. Okay, well, I would change the slope and then ask you what is the resistance. I guess I could also give you the a graph of, what would that be, I and V, and then, oh no, that's what I have right here. Give you a graph of V and R and ask you what is the current. Yeah, so it'd be the slope, and in that case, the slope would equal to the current. Or if it's one like number 10, if it's number 10, I would likely just change some of these numbers, and then you would have a different material to pick from. Let's see, what's another good example? If it's a circuit like this on number 12, it would be a different circuit, but it would be of similar difficulty. So for example, I might give you this question, but instead I might give you, I don't know, a circuit that looks like that. That's a circuit that's of similar difficulty. It still has 3 resistors, but they're arranged in a different pattern, but it does have both series and parallel components. So when I'm looking at these questions, I want to say, you know, from my perspective is I want to make sure that you can show the same skills in answering that question. And so that's how I'm going to change it, but with the idea that you're still showing the same skills. So as you're working through the exams, don't just say, did I get the answer right or not? Like, that's not really good enough. You want to say, do I understand how I got the answer? And then if you really do understand, then you'll be able to apply it in other situations that are similar. So that's what you're looking at, is other situations that are similar. These show bright to least bright. I could also ask you to rank, you know, the currents or the voltages. That would actually be the same. Or I could give you slightly different bulb configurations. Like for number 17, I would just give you a different circuit that has different currents in it. All right. So that's sort of the idea as you're working through the old exams. But that's what you should do, is you should focus on the old exams. And then if you mess up on some of those questions and you're not really sure what's going on, then go back and look for those kinds of questions in the previous exams, because they're there, at least in the last decade or so, that if you find a question in this exam, then you're going to find a very similar question in a past exam. It'll be different, But then that way it'll help you to, say, well, first, what are some ways that he can change these? What is it really assessing? And just give you additional practice. So start with this semester's exams. If you make 100% on all of those, then you're probably good. If not, then start digging back into the past exams. All right? What are your questions? Yeah.
It doesn't really relate to this, but are you going to give us to make an A, to make a B, to make a C?
No. If you want, you can email me. I can tell you. No, that's just for drop day.
While we're here, let's just do the exam 1 trick-to response.
The free response, the one that's going to be on there? Okay.
Yeah, might as well.
Yeah, you really want to, I find that students that do well on that question, that they, and it just sets a good tone for the entire exam. Oh, what happened? Okay. I'll just leave that. All right. So I want to know what is the magnitude of the electric field, and then what is the electric potential. The magnitude of the electric field is the harder part. First, draw my coordinate system right there. Now I'm going to draw my electric field vectors. So in order to determine the direction of the electric field, I imagine a positive charge at that location and ask myself, what is the direction of the force? And then that'll be the direction of the electric field. So here, if I have a positive charge, it will feel a force that is repulsive from that Q1. So that is the direction of the electric field. And then due to Q2, it will feel an attractive force. So that is E2. Then I also need to know this angle. I can look at my triangle right here. This is 3, this is 4, this is 5. This angle right here is 37 degrees. You can use your tan function to find that. Inverse tan of 3/4, opposite over adjacent. So that angle is 37 degrees. Then I calculate E1 and E2. I'll give you nice, easy, round numbers. You shouldn't even really need a calculator for this part until you get into the components. So that's going to be for E1, KQ over R squared, 9 times 10 to the 9th, 32 times 10 to the minus 9, divided by R squared. That R is 4 meters, so that's 4 squared. And then look, I get some cancellations. These cancel. That's 16 into 32 leaves me 2. And so that leaves me with 18 volts. It is positive because that 32 is positive. Or excuse me, never mind. There is no sign attached to it. That is just the magnitude of that vector. Yeah.
How is 4R?
How is 4R? R is the distance from here over to here.
Okay.
And so it's the same as what's right there. Then for E2, I need to know this distance. That's a 3, 4, 5 triangle, so it's 5 meters. So it's going to be 9 times 10 to the 9th, 25 times 10 to the minus 9. Notice I don't put the sign on that, divided by 5 squared. I get some cancellations, there, and there, and that leaves me with 9 volts. So you'll have similarly easy numbers, just that it'll cancel out. Chloe?
Could you remind me, how do you know when to use like the sign?
Anytime you're dealing with vector quantities, you do not use the sign. That includes electric fields and electric forces. The signs come into play, but when you're drawing the vectors, like when I was trying to figure out the direction of the vectors, I said, oh, it's a negative charge, so it's repulsive or attractive or whatever. Anytime you're dealing with scalar quantities include V and PE, potential energy, that you do use the sign. All right, because the sign there talks about, am I giving energy or taking away energy? Remember how we had work, when we back last semester we did work and it said it could be positive or negative even though it's a scalar quantity? That's what it means. It means you're giving energy or taking away energy. So V and PE, use the plus or minus signs. E and F, those are vector quantities, so do not use the signs. And you'll see in the equation sheet that there are absolute value bars around Q. That's to remind you that you don't use the signs. All right, so now that you get these vectors, now we need to know E2x and E2y. That's E2 cosine of 37, and E2y is E2 sine of 37. So you know how to do the x and y components. X is cosine, y is sine. So E2 is 9. That's 9 cosine of 37. That's 7.2. And then 9 sine of 37 is 5.4. Okay, so now you draw your resolved vectors. That's going to be E1 is 18. I said volts, I'm sorry, this should be newtons per coulomb. 18, and then E2x is 7.2, and then E2y is 5.4. Then I find, I do 18 minus 7.2, that's going to be 11.8, I'll just call it 12. And then this is 5.4. Yeah, to get the 12, I said 18 minus this number, and I got 11.8. Then I do the square root of 12 squared plus 5.4 squared, and that's my answer. So there are about 4 steps right there. Drawing your vectors, calculating the magnitudes, calculating the x and y components of the one off-axis vector, and then resolving those x and y components to get the x and y components of the electric field vector. I guess there's 5 steps. And then find the magnitude of that vector. It's something we've done a bunch, though. Like in the last year, we've done these vector problems a bunch. I know not so much in the latter half of the semester, but it is very important to me that I see that you can do vector math. Okay? The next part of that is to find the potential. And the potential is a little bit easier. It's just the sum of the individual potentials. That's K, hey Chesney, KQ1 over R1 plus R1 plus KQ2 over R2. And you put in the values for Q, that's plus 32 and minus 25. And you put in the values for R, that's 4 and 5, and you solve for that potential. Y'all okay leaving that? Can y'all do that on your own?
So
V is potential, yeah, or voltage. That's another word that we'll use. So anytime you see V, think potential or voltage. Okay, I can do that, but I think y'all are probably okay doing it.
Use the signs for that.
Right, you do use the signs. Anytime you have scalar quantities, use the signs. Anytime you use vector quantities, do not use the signs. And again, you can see this on the equation sheet. You'll have the full equation sheet. And if you notice, where is it? Like right here for electric field, see, no signs. Likewise for force, no signs. Then down here for voltage or potential, you do use the signs. There's no absolute value bars. And same for the potential energy. So if you forget, just look on that equation sheet and look for those absolute value bars. All right? What else would y'all like to do? I could go through, but there's so many questions. Something happened here. I lost my exam. I'm going to reopen it. Particular exams, particular questions. I was hoping other people have questions. Yeah. I can sort of skim through them, and let's just sort of skim through exam 1, and then y'all look. I know you've probably been focusing on your other exams. So exam 1, you know, there's the free response to that. There's basic stuff about charges and charging, conductors and insulators. There might be some like this where I'm actually finding the direction. There's these relationship type problems where I ask if you change something, how does that affect the force or the electric field? There's these things about how does the force or electric field go to zero? That's number 7 or 12. Yeah, students had difficulty with that. So when you encounter one of these, and there are 2 that are similar, number 7 and 12, so, you know, pretty good chance you're going to get one of those. Then where can you place a charge so that the net force on that charge is 0? And it's either positive or negative. You imagine that you have a positive charge here and ask yourself, you know, is it possible to have a 0 force on that one? Actually, that's the answer, so let's not do that one first. Let's do it over here. So imagine that it's positive over here, and notice that I have a really big force attracted to the negative 4q, because I'm really close to that big charge, and then I have a little force that's repulsive from the plus q charge. It's a little charge, and I'm far away from it, so it's a little bitty force. I'm never going to get a 0 force there because the one force is always going to be bigger than the other force. So it can't be to the right of the minus 4q. Likewise here, if I'm in the middle, I have a big attractive force and a repulsive force. So no matter where I am in between the plus q and the minus 4q, they're always going to be in the same direction, so they're never going to cancel out. So I can't be at x or in between plus q and x or in between minus 4q and x. So that leaves only b. Notice here I have a repulsive force from plus q, and then I have attractive force to minus 4q. But because I'm farther away from minus 4q from the bigger charge, then, yeah, in general, not always, but in general, on these types of questions, you want to get as far away as possible from the big charge, because being further away increases that distance, minimizes the impact of that bigger charge. So I would always start in the place that's farther away from the big charge, and then just work through it and make sure that that's, you know, that actually works, thinking through how to draw those vectors. And, you know, I know the direction of the vectors. Like charges repel, opposite charges attract. If I'm doing electric field, I imagine a positive particle there and ask what is the direction of the force, and then that is also the direction of the electric field. Yeah.
Remember 11, what's the other option you said you could give us besides electric?
Well, there were 3 big ideas in that chapter: electric forces, fields, and potential. I mean, a force is just a force, of course, but a field is a force per unit charge, and potential is energy per unit charge. Those are our 3 big ideas. So yeah, I could change that from fields to potential and still expect you to know those 3 big ideas. A field is a force per charge, potential is energy per charge. And then there was the forces, which we'll also see. All right, these things where we're doing forces in 2D, but, you know, conceptually, there's a good mix of conceptual and calculating problems. And I tried not to pick all the hardest problems, so I tried to have a good mix of those problems that I'm hoping will be, give me problems that they're relatively easy and straightforward. Yeah, number 13. Oh yeah, so on this one, you really just have to go through all of them. The charges are the same size. There's no way to get farther away from the biggest charge. So I imagine at each location a positive charge and ask myself, what is the direction of the force? And so I'll do the one up top first. It's in that direction, and there in that direction. It doesn't matter what their relative sizes are because they're not opposing one another. If they were opposing one another, I would have to think about what are their relative sizes. But actually in this one, there are no locations where they are ever opposing to one another. The vectors are all like that. See if you can identify which is to which charge, but they will all look like that.
So you could give us one that's
I could, yes. So, I mean, don't assume that that's the case, but yeah, I could I wouldn't give you like 3 charges. That sort of gets kind of quite a bit more complicated, but I could move them around in the space. And move the dots around. Though with this configuration, there never is a spot where the electric field is 0. Isn't that right? Yeah. Yeah, there's never a spot where the electric field is 0. But I could change the charges up and, All right, let's keep skimming. Electric field lines, where are equal potential lines, or where is our potential 0? Y'all just pause me. There are these equal potential maps, like
The map.
yeah, the map. So this is like a topographical map. Y'all don't do land navigation anymore, huh? In high school, they don't teach that. Compass. What? You have a compass on your shoe?
Topographic line.
Oh yeah, so those topographical lines, they're like a topographical map. So here I see that my electric potential is increasing, so I can think of this as like a mountain, and here the electric potential is decreasing. I can think of it as like a valley, right? That it goes from -4 and getting more and more negative. I'm releasing a positive charge. Remember, positive charges roll downhill. Negative charges will tend to roll uphill. But positive charges move from high to low potential. I want to know how much energy does it reach when it goes from point A right here all the way over to point B. It is going to move from A to B. It's like it's moving downhill. It's actually moving downhill and then moving into this valley right here. So as it moves from A to B, the change in potential there is going to be, well, it's moving from final is -6, -12. I did VF minus VI. That's -18. The negative is irrelevant because I'm just looking for the energy that it gains. But the energy that it gains, I'm going to call it U, is equal to Q times delta V. If you remember, V is energy per charge. And so that's just a rewriting of that equation. I think that is on your equation sheet, by the way. So I have 2 coulombs times my change in potential, which was 18 volts. So it's going to be 36 joules. But you do need to know how to read those topographical maps. I think there was actually another question that was similar to this, where you had a topograph, or it's not a topographical map, but it's like it's a potential map, and it's like a topographical map. Can I clear this?
Yeah.
Yeah. All right, let's see.
Go back to 17.
Uh-huh.
Can we show what it would look like?
Sure. Yeah, so on some of these, actually, it is 0 at a particular point. Like on B, the potential is 0 right there because this distance is equal to that distance. So the potential of those 2 opposite charges cancels out because it's KQ over R plus KQ over R, and one of the Q's is negative, and the R values are the same. Likewise, here and here, those 2 cancel out. But over here, those distances are different. A situation where it would cancel out would look like this. +2, -2, -1, +1, or +1, -1, all along this line. Notice here, at this point, this distance and this distance are the same, so the potential due to those 2 charges cancel out, and that distance and that distance are the same, so the potential of those 2 charges cancel out. That's true all along this line. By the way, that's also true along this line, isn't it? Oh wait, no, it's not. No. Here, if I'm here, these distances are different. So along the x-axis, there is an equal potential line where V is equal to 0, but along the x-axis, the V is not equal to 0. In fact, that's not an equal potential line.
What about the distance between +2 and +1?
That doesn't matter because the +2 and the -1 are not going to cancel out. So even if the distances are the same, the bigger charge will dominate the potential. Okay. Yeah, so you're just looking at the equal and opposite signs. All right. Let's go to exam 2. I think that was mainly circuits, capacitor, resistor. You're going to have one or two on this. I want to see a circuit. I want to know that you can do a circuit. So you'll have one or two. And then there are a lot of circuits in the exam too. Some conceptual, some calculating, where you're actually calculating a capacitance, a charge, current, a voltage.
Can you do 11?
Mm-hmm. Yeah, so here you're supposed to calculate the resistivity. And remember that R is equal to rho L over A. And so the resistivity is RA over L. I think you first have to calculate the resistance, which is V over I. That was 10 divided by 5, or 2 ohms. So rho then is 2 ohms times A, which is 1.7 times 10 minus 8, divided by L, which is 2. So that cancels there, and I'm left with 1.7 times 10 minus 8, so it must be copper. I try to make the math as easy as possible, okay? Some problems will require a calculator, but I try to not have a calculator at all.
And how'd you get the resistivity?
The resistivity?
And
The resistance?
yeah.
I just use Ohm's law up here. The resistance is V divided by I. That comes from Ohm's law, V equals IR. I solve for the resistance. So R is V over I. This is V right here. This is I right here, the current. 10 divided by 5 is 2. Like on this one, I wouldn't change it except for the numbers. It would just change it up a bit with the numbers. Will be, I think, a fairly even mix of conceptual and calculation on this too. I want to know that you know your rules. I want to see that you can apply them. I do want you to be able to calculate things as well. Remember with these, when you're looking at potentials, it is useful to just understand how those potentials are distributed. So for example, here I have these 3 resistors, 4, 8, and 12. And I know that the 12 ohm has to have a big voltage, and the others are going to have a small voltage. So I could probably get rid of these 3 at least, and then I could go through and think about what the others, like if I said, well, if this is 6 volts, that means this is 3 volts. And if that's 3 volts, then that means that this is 6 volts. Well, no, it can't be 6 volts. Maybe it's 4. Is that right?
It's probably going to be 8, 6.
No, it is.
2.
I think 4 makes sense.
Oh, no, I'm sorry. I did this wrong. Yeah, I think if that's 6, yeah, if that's 6, that means this is 3. And if that's 3, that means, oh, shoot, did I do this wrong?
Ratio of 3, 2 to 1, and then be like,
It'd be 8, 9, 10, 11. Wait.
Yeah, no, that's not making sense.
Potential plus 12.
there'd be 6.
Wait, what's the answer?
Oh, no, this would be,
Do we even need the other ones?
oh,
Yes.
oh, y'all are confusing me.
The other ones, I thought. You just need the 12. So if 8 and 4 is another 12, then they split evenly 6 and 6.
Wait,
Smart.
Can't you solve?
Well, look at you.
Oh,
Look at you.
She's smart.
I was gonna put other.
Y'all see what she did? That was very clever. She said, well, these two, oh, these two have an equivalent of 12 ohms, so it's really just like I have a 12 ohm and a 12 ohm resistor.
so it's 6 and
So
6.
it's 6 and 6.
So it's
You
6
don't
and
even
6.
need the 8.
You don't even need the others. Man, look,
We're not
look
even
at that.
solving for 4 and 8.
That's what I was. Yeah, that's what I was looking at, trying to figure out what was
Which
going
would
on.
be 4 and 2, though. You were getting
Yeah.
confused. It would be 4 and 2.
It'd be 4 and 2, right. Mhm.
You put that 3 up there, we were all like,
Yeah, because this resistor is 1/3 of this resistor, so the voltage is going to be 1/3 of 6. And then this resistor is twice this resistor, so it's going to be 4 volts, twice that voltage. And then I can add them up, 6, 4, and 2, and that adds up equal to 12. So just knowing those little tricks will really help you. It'll help you on the conceptual stuff too, if you just know how the voltages are distributed. Joey?
And for resistors, the voltage is, what is the word? it's like following the same trend, but for capacitors, it's following like the opposite trend.
That's right. For resistors, the voltage is directly proportional, following the same trend as you say. And for capacitors, it's inversely proportional. The voltage is inversely proportional to the capacitance. So big capacitance, small voltage. Big resistance, big voltage. It's good to remember. It's a tough exam because we've covered a lot of material this semester, even though we didn't get that last chapter, that we've covered a bunch of material. But I'm confident that, for y'all going on to do various standardized tests, though, that you'll be in a pretty good position to be prepared for those. So I think that's good. That's our goal. All right, let's look at exam 3. Multi-loop circuit, RC circuit, and magnetic fields.
Can we do 2 real quick?
Mm-hmm. You can probably guess that if I'm going to give you a circuit in the previous exam, then what am I going to give you from this exam? Number 3. Gosh, I'm giving away so much.
Oh man.
Oh man.
Let's just do 3.
Yes,
I mean, don't speculate on what I'm going to give you for the free response, but if I'm giving you a circuit from exam 2, the capacitor or the resistor circuit, then I'm not going to give you another circuit from exam 3, right? That would be foolish. All right. Okay, yeah, so number 3, well, the direction of the magnitude of the magnetic field at the location of the proton. So I want to know, what is the magnetic field at that point? Remember, B is equal to mu naught I over 2 pi r. I think that's right. Let's just go look at the equation sheet. I don't remember this one.
That sounds right.
Yeah. Yeah, it's this one right here. Remember, there are 2 equations that look really similar. This is for a loop of wire down here. You can tell because it's the N. But the one for a long straight wire has a pi in it. So, where is it? So I can calculate that. Mu naught is on your equation sheet, 4 pi times 10 to the minus 7. I is 4 amps divided by 2 pi. And then R is this distance, 0.2 meters. I can cancel out a few things. Those pi's go away. This 2 goes away with that. And I get 840 times 10 to the minus 7. That's Tesla. Okay? Isn't that right? Yeah. Then I also want to know the direction. So you have to get both of those in order to get it right. This is pretty easy, just plugging in numbers. You get the direction, you let your thumb go in the direction of the current, and then it folds around so that it would be into the page on this side and out of the page on that side. So at the place of the proton, it is in the plus Z or out of page direction.
You're always going to use the side that's one side of the proton.
Yeah. Because, I mean, there are 2 magnetic fields generated. Here it's out of the page. On this side is into the page. Now, in this problem, if you were to see it on the exam, wink, wink, I can't wink my eye, then I could take that figure and mess it around and just sort of reorient the charge and the wire, make it an electron or whatever. I could change it in various ways, but it's still going to be the same process. So like if the proton was on the other side of that wire, then the magnetic field would be into the page. Now the next thing that you want to do is to figure out the direction and magnitude of the magnetic force. So for part B, to find the magnitude, that's fairly straightforward. It's just QVB. You know the magnitude of the charge, 1.6 times 10 to the minus 19, that's fundamental unit of charge. I give you the velocity, and now you know the magnetic field. So you calculate that force, and then to find the direction, well, I have a velocity vector that is in that direction. I have a magnetic field vector that's out of the page. I like to redraw it like that so I get it out of all the messiness of the figure. V is down, B is like this, and so it's going to be to your left. So my force then is in this direction. Check, make sure it's still a proton. It is, so that means that the force is to the left. Remember, if it's a negative charge, just put a big circle around it as soon as you read that, and then remind yourself to go back and change the direction. I'm pretty sure you do see some negative charges, huh?
Just as the force.
You're right, just for the force. Okay?
Can you go over the left-hand rule again?
The right-hand rule?
I mean, yeah.
Yeah, the right-hand rule. Yeah, so there are two basically applications of the right-hand rule. The one is where I have QVB or F equals ILB. Both of those are basically the same. Your index finger goes in that direction for V, R for I. Your middle finger goes in this direction. Finally, a good use for that middle finger. And then your thumb goes in the direction of F. All right. So, for example, if V is in this direction, B is in this direction, B is down, that means that the magnetic field, or excuse me, the magnetic force is into the page. All right.
Oh, it's out of the page.
No, into the page.
Yeah, my bad.
All right. Okay. And then the ILB, that works much the same, except you're letting your index finger go in the direction of the current. So I could replace this with a wire, and it would be the same. And then there's the one where we're letting our thumb go in the direction of the current. So if I have a current like this, my thumb goes in the direction of the current, and then the fingers wrap around and show the direction of that magnetic field into the page on this side, out of the page on that side. But you can orient that wire in any direction that you want, even coming towards you. Like if I have a wire that's coming towards me, my magnetic field would look like that. That would be my magnetic field. My thumb coming out towards me, and then my fingers wrap around in a counterclockwise direction.
That's what we did in part A, huh?
Yeah, that's what we did in part A. I like this one because you use both of those applications of the right-hand rule. Not saying it's on the exam, but okay. But it is on the exam, so that is one of your free response.
Like you've already written the exam?
Yeah, I'm actually not going to be here on Monday. Oh man, I might be here. Did you just sigh? I'm going to South Lafourche, and if I get back in time, I have the best wife in the entire world. Nobody has a wife better than me.
Teachers administered the majority of our exams.
3 of 5, yes.
And the final last semester.
Oh, she did that?
Yes, she did. She did the final last semester.
Well, I've had 2 funerals, and this is a recruiting thing, so. All right. Yeah, you can write on your fingers, that's fine. You get it tattooed, you get extra points.
How many?
I don't know, 2? 2.5?
Does that go on top of us maxing out?
All right, household things.
For the questions like number 2.
Yeah.
How do you know whether they're negative or I guess like number 3?
Number 3. Oh, okay, yeah, so you do need to know those rules. And you know, I told you you're not going to have this one, so that means you're definitely going to have a multi-loop, and probably a couple of multi-loop in the multiple choice. So you need to know those rules. If I'm going through a resistor, say the current's in this direction, and if I'm moving in this direction, that's going with the current, then the change in potential is negative IR. If instead I'm going against the current, the change in potential is equal to positive IR. In general, you don't go against the current in a circuit, that you go with the current. But as you're analyzing a circuit, if you're going against the current, then I think, well, a resistor does the opposite of what you would expect to do. Resistors are always devices that consume energy, so they have a negative change in potential. For batteries, if I'm moving in this direction, I have a positive change in potential. If I'm moving in this direction, I have a negative change in potential. Doesn't matter about the direction of the current. All it matters is if I'm moving from the little side to the big side. If I am, that's positive. If I'm moving from the big side to the little side, that's negative. So I always think of the little electrons on a roller coaster, and they're going up, and it's like jugga, jugga, jugga. They're gaining energy, but then when they're going down, it's like whee, and they're losing energy as they go down the slide on a roller coaster. So gaining or losing energy. Those are important to know. So here, for example, you could apply that. Let's just look at equation B. I have minus 2I1. That means that I'm starting here and going in this direction. I1 is in that resistor, and I want to go with the current in order to get the negative. So minus 2I1 minus 6. That's correct because I'm going from big to little. Minus 9I2. That's correct because I'm going with the current. And then I have plus 3. That's correct because I'm going from little to big, from low to high potential. So that equation is correct. B is. So, if that's the case, I can get rid of these 3 answers. And now I'm down to just, is C correct or not? Trying to look for those little shortcuts. Those are great tips for how to take a standardized test, a multiple choice standardized test. Eliminate your answers as early as possible. Often on my exams, you can eliminate all but 2 fairly easily if you have any understanding about the concepts at work. But you don't always see that because you go into the exam and you're just stressed and you're anxious about things and you're not thinking clearly. So y'all really try to relax during the exam. Do whatever you need to do to relax. I mean, no, not whatever you need to do. Try to relax during the exam.
Not too much.
But not too much, yes. All right? Let's see. Y'all stop me, holler if you see something. Moves in the magnetic fields. There was 13. Oh yeah, a lot of people miss that one. But I like it because it's 2 applications of my right-hand rule. So the first thing is to figure out what is the magnetic field at point A. Is it about 13? Bryce? Bryce, I'm sorry. Is it about 13? Or are you just stretching? Okay, all right. Find what is the magnetic field at that point. So take this charge, for example. I like to draw a radial line. It's into the page. That means the magnetic field is in that direction. Due to this charge, it's in that direction. And due to that charge, it's in that direction. That means that my net magnetic field is in this direction. The x components of that blue and red vector, they cancel out. But yeah, that's right, they cancel out. So your net vector is in the downward direction. Now I have a different problem. I have a current that is out of the page, a magnetic field that is downward, and I want to know the direction of the force. So index finger in the direction of I, magnetic field is down. That means that the force is like that. That's to the right.
Okay, so could you kind of explain how you drew the arrows?
Yeah, so that's that second application where you're letting your thumb go in the direction of the current. Let's just do one. I'm going to erase everything on here. Let's just do this one right here. So like I said, I like to draw a little radial line because I know that if I draw that radial line, my magnetic field either has to go in this direction or that direction. It has to be perpendicular to that line. So I imagine my thumb going into the page, and then it wraps around so that the vector is down in that direction. the vector is going to be tangent to that circle that you draw. But because it gets difficult to draw those circles and they start overlapping, I usually just draw the radial line and then draw a perpendicular vector to that radial line. Okay?
And if they're, like, they don't cancel out if they're across from each other, but they cancel out.
Yeah, so if like I had before, I had two vectors like this, and then one vector that's down. So if I have two vectors that are equal and in those directions, they both split into components that are like that and like that. And these two components cancel one another out. So I have no x component. That's what you're going to be looking at, is looking for components that'll cancel out. So your net vector will only be in one direction. It is great.
Real quick, do 12. I know we just passed it.
Yeah, the magnetic pole of the Earth nearest the geographic North Pole is the southern magnetic pole. So on the Earth, here's Florida, here's Africa, this is Antarctica, this is the Arctic. So this is the northern geographic pole and the southern geographic pole. But if I think of the Earth as being like a big magnet, the southern magnet, the southern end of that pole is up top, and the northern pole is at the bottom. So when I use a compass, and I have a little compass right here, the North Pole points towards the northern geographic pole, and the South Pole points towards the southern geographic pole. And so the compass is, that's why we call those North and South poles on a compass, what they are. You follow what I'm saying there?
So it's B.
B is the answer, right?
Yeah, okay.
Magnetic South Pole. They don't perfectly line up, but they're in the same general area. All right. Several students have asked me about this. I have this on the text, but there was a discrepancy between the text and the figure I gave everybody. I think the answer in the test takes the figure into account. All right, let's look at exam 4.
Wait, like,
One more.
okay.
So the text says that the magnetic field is out of the page, but the figure shows that it's into the page.
And how would that affect it?
Well, it changed the sign from whatever to whatever, from positive, negative, or negative to positive.
Right, and how?
No, we'll just answer it. So imagine the charge at some point is moving with a velocity vector in this direction.
Yeah.
The magnetic field is into the page. So V is down, magnetic. So that means that the force is in this direction, which is the way that it's drawn, that the force is a centripetal force, which is always center seeking. And so that means that this is a positive particle. Okay, but if it was into the page or out of the page, then the force would be in this direction, which would mean that it would be a negative particle. Because the force is actually towards the center of the circle, and so you can tell then, is this a positive or a negative particle? All right, let's go to exam 4. I'm gonna have to leave at 4. Okay, so a little bit after. Never had a health session this long. I have lots of questions.
It is for the final, so.
Yeah.
Yeah, it's.
All right. Well, and no hints on this one. They're all optics, and I want it to be optics. So, y'all okay on these? This is pretty fresh.
Ask that when you go down to 2, when you do 1.3 sine theta, the angle is that as it's going from 1 in 1 sine theta equals in 2 sine theta. The angle that goes within 1 is as it's going from 1 to 2, or is it?
That would be this angle, yeah. And this would be this, and I'll call this theta 2, this theta 1.
Okay.
In fact, actually, these two angles, this is also theta 1. Those two angles are equal. They're, what are they called? complementary angles, or no, not complementary, or something.
No, that's right.
Is that right? Is that right?
I think so.
Anyway, they're equal to one another. Did you have missed a lot for geometry? Joey? Missed a lot for geometry?
Mhm.
My daughter's in that class right now. She loves it. Loves geometry.
So can you do number 2?
Yeah, it was an easy question. My wife said, all these students were asking about number 2. And I looked at it, it's like, man, that's like the easiest question on the test. Because the answer is 60 degrees.
Yes.
I got 50, I can't lie.
Yeah, I know a lot of people miss it. So don't be ashamed of it. But, I know that N1 sine theta 1 is equal to N2 sine theta 2 is equal to N3 sine theta 3. I could call this N0 sine theta 0. And I want to know, what is this angle? Well, look, this is still N0 sine theta 0. And so I could say, I could set these two equal to one another, but since the indices of refraction are the same, air is equal to 1. Several people ask what's the index of refraction of air, but you do need to know that. It's equal to 1, right? So then the angles theta are also the same. Some people actually went through and calculated every single angle, and I applauded them, but that was a lot of work.
I did that when I had time.
You got the right answer, right?
Yeah.
What was it?
I did that when I had time at the very end of the test, just to check that it actually was 60.
Yeah. So
how would you draw it?
oh, how would you draw it? Okay, yeah, let's do that. That was part B that I was talking about. To trace it, you want to ask, is it moving faster or slower? So here, n equals 1. That's fast. And this is slow. So as it goes into the slow part, this part turns around. It bends towards the normal. Here now, it's moving from slow to a lower index, which is fast. So here it's going to move away from the normal, like that. And then it's going to bend towards the normal because it's moving into a slower medium and then away from the normal. It's going to end moving in the same direction as it started. We saw that in lab too, by the way, with the glass slab. Your two rays were parallel with one another. They were just offset from one another. I am recording this, right? Yes. Okay. All right. Let's look here. Reflection. Know your different types of light. Remember I said I wouldn't ask about the people, Huygens or Newton. Somebody locked me into that. Huh? Yeah. Okay, so law of reflection says that these two angles must be equal. If that's 40, that means that this angle is 50, because they should add up to 90. And then if 110 and 50, that's 160. That means this angle must be 20 degrees, which means this angle must be 70, which means the final reflected angle is also 70. That's what I want to know.
The biggest from the smallest is always the greatest. Like 110 times 1 equals 70.
Yeah, that might be right. That does. Might be.
That was wrong.
And you just realized this?
I think that's just the laws of geometry that work.
Yeah, I think we should ask Ms. Delat.
She should.
There's probably a note card for that. Huh?
Don't remind me of
I'm not sure who went to Thibodeau High. Who went to Thibodeau High? Just you? Okay.
Don't remind me of her note card.
No, my daughter loves them. She loves the note cards. All right. Just skimming here. Y'all holler if you see something.
So number 9, when it's dealing with the color, is chromatic.
Yeah. And if it's not color, it's spherical. Right. Chromatic means color. So if you see colors, that's chromatic. Make sure you can calculate F, P, and Q. Make sure you know those different types of images that are formed. That comes up a bunch in this exam. So it's probably going to be important for 4 or 5 of the questions from this exam. There are 10 total. You know how to draw your rules. Right. The flatter the mirror gets, the bigger the focal length gets. Likewise for lenses, this has a really big focal length. This has a really short focal length. You can tell from just the curvature of the lens.
For number 9 with the spherical and chromatic, even if it's colored light going in at 2 different locations.
I wouldn't do that. That would be confusing. Yeah. It's either gonna. I mean, that would be a combination, right, of spherical and chromatic aberrations. I wouldn't do that. Or would I? No, I wouldn't.
See, I thought that was 2 separate locations.
Oh, really?
Yeah, I kind of,
So I put spherical.
I put chromatic because I was like, it's 2 different colors of white. But I almost was like, it's kind of going in at 2 different spots.
Oh, I'm sorry. Y'all should have asked me. Oh, wait. I wasn't there. You could have asked my wife. She would
I
know.
didn't even realize it had the colored light on
Yes,
it.
you could. That's
I
why
literally, I looked at the lens
I
itself
didn't
and
realize
said 2 different locations. Spherical.
I'm like, wow.
Okay.
I saw red, blue, I thought colors chromatic.
Yeah, I put chromatic because I thought red and blue was the defining factor there. But
You have the right idea.
I
Bethany.
completely understood what you did because
I hear you. And you know, if it was going to affect the overall grade, I would be concerned about it, but it's not. Nobody's ever separated from a B to an A or B to a C because of 3 points. It just doesn't happen. I don't allow it to happen. Okay. All right. Is that all?
And number 7.
7? Yeah, for total internal reflection, you always have to be moving from a high index to a low index. So if this is like a fiber optic cable, I always like to think it's a piece of glass. It's a thin strip of, or a thin strand of glass. The glass is a high index of refraction. The air around it is a low index. So it must be traveling into a medium with a lower index of refraction. If it's opposite, then it doesn't occur. It bends towards the wrong direction.
we didn't scroll all the way to the bottom.
Okay. Ooh. Oh, no, I didn't want to do that. All right.
Oh wait, 19. What was the correct?
Which ones are drawn incorrectly? This one's parallel and through the focal point. That's correct. This one's through the center of the lens, unrefracted. Here's through the focal point and parallel. All are correct. You can tell too, they all cross at the same point. You get the kind of image that you would expect, real inverted image. So I feel okay about that answer. Like if I've just answered all are correct. All right. Is that all, y'all?
Yep.
There's some